So hello everyone, welcome to today's seminar, and our speaker is Professor Hopkins from Caltech, and he's spending his sabbatical vacation in this semester, and he has done many important work in astrophysics, including star formation, galactic formation, of the cosmology simulations. And today I think he will also give a very interesting talk about the supermassive black hole from million parsec to AU scale. So I will give this back to Philip.
Hi, everyone. A bunch of you, but hello to those of you I don't know or looking forward to chatting. I'm here for this semester. So this talk is partly to talk about some things, some recent results I'm very excited about and try and explain some of them since I don't expect even the people who are very interested in this to be, reading 110 archive papers a day to keep up on all of this, but also to sort of advertise just things to talk about for the coming term if you're interested in any of this. And I mentioned in the call lunch, for those of you who were there, a bunch of the other topics our group has been working on. This is going to be a deep dive on one of those topics on the growth and accretion of supermassive black holes. So how do we get these monsters in galaxy centers? And even that I'll have to restrict a little bit what I talk about. And I'm just going to very briefly introduce this because I'm going to assume most of this audience is familiar. And we also had talks by Reinhard Genzel last week and by Priya Natarajan just on Tuesday, talking about massive black holes and galaxies, also doing lots of the setup. So of course, we know that supermassive black holes reside in most massive galaxy nuclei, and these are some of these beautiful movies, like the kind of observations Reinhard talked about mapping out here. The star's orbits around Sag in the center of our galaxy. We see, AGN having a huge effect on galaxies in quasars and Seyferts and radio galaxies. Famous examples of giant radio jets and winds and outflows affecting the whole galaxy. And of course, we have new types of observations probing down to horizon scales, these beautiful images from EHT, and future planned observations with facilities like LISA, observations from PTAs about information that potentially goes down to those horizon scales. But the challenge with much of this is that there's not just a huge range of physics involved, but there's a huge range of scales, right? So just to give some grounding for typical supermassive black holes, the horizon scale is sort of an order AU, and the scales out to which the AGN can affect the medium and from which the AGN is ultimately getting its gas that will feed it are of order megaparsecs. So there's a huge scale separation built into this problem that we need to deal with. And that's the two things that, again, make this problem really challenging. It's this huge scale separation in both space and time and mass. And then also it's a fundamentally multi-physics problem because many of these scales depend on the interplay between radiation, magnetic fields, gravity, thermochemistry, and then on larger scales, things like star and galaxy formation, and all these feedback processes that couple them. And as a result of these challenges, and these are not just theory challenges, but observational challenges as well, because it's hard, you can't simultaneously resolve these scales observationally either. And you can't measure a lot of these with the same types of probes. And some of these are incredibly difficult to get any kind of measurement of observationally. So we still have really zeroth order questions that remain open. Where do supermassive black holes come from? What are the seeds? That's a lot of what Priya talked about. How do they actually grow? And how does their accretion relate to their environments? And then what do they do to their surroundings, what we call AGN feedback? How do they impact their surroundings? In this talk, I could easily give a whole talk about it. I'm just going to show one slide advertising some students' results because I don't have time to go into it. And I'll spend a couple minutes on this, mostly just as transition to this. My main focus is going to be on how these things grow in this talk. So the seeds thing, I just want to set up by maybe giving a defense of rapid growth of small seeds for those of you who saw Priya's talk. So I think, it's commonly said, and she argued this very strongly, that high redshift supermassive black holes being present favors these sort of direct collapse models. Essentially models where you skip the queue and go straight to supermassive black hole. You just have some exotic process that makes a 1,000,000+ solar mass black hole already. It's also commonly assumed in models that black holes sink efficiently to galaxy centers via processes like dynamical friction, scattering off of background objects, and then are able to grow once they get to galaxy centers. And I think both of these are not really so solid a conclusion for reasons I'll briefly describe that set up some of the problems I care about. So in terms of growth, let's just remember if you're growing at some fraction of the Eddington limit, so say F duty is the duty cycle, the fraction of the time your black hole is growing. Lambda ed is the ratio, the Eddington ratio, how far above or below the Eddington limit you are. Delta T is the time you've been growing. And M initial is the initial mass of your black hole. This will be the mass of your black hole at some later redshift, given some initial mass. You want this to be big at some early time. You have two choices, basically. You can either have a heavy seed, you make this number big. That's the sort of direct collapse or very massive, supermassive black hole seeds argument. Or you make this number big, which is the sort of highly super Eddington accretion argument. Because if this number is small and this number is small, you have no hope of making the black holes be observed at high redshifts. Now, the problem I would argue with doing this is that this number is outside of the exponential, this number is inside the exponential. So it's a heck of a lot easier, I would argue, to do this, to get a big black hole with this than with this. Because this doesn't have to be enormously big, basically, whereas this really does as we get to higher and higher redshifts and bigger black holes. So to give you an example of that, so if you assume you're Eddington limited and have a duty cycle of 1, meaning you're accreting all the time, but you're restricted to the Eddington limit, you can ask, how long will it take to grow, say, a 10 to the 9 solar mass black hole from your initial conditions? Well, if you start from one of these supermassive seeds that's already 100,000 solar masses, it will still take you 500 million years to grow this thing to 10 to the 9 solar masses. If you start from 100 solar mass black hole, it does take you longer, but it only takes you 800 million years. It only takes you logarithmically a little bit longer to get that big. Whereas if you say instead, I'm going to allow myself to accrete at several hundred times the Eddington limit, but only for a small fraction of the time, just 1% of the time. Well, then I can do it in less than 100 million years with either of these channels, basically. And that's just, again, inside versus outside the exponential is the difference here. Maybe this is assuming you go up to 1,000 times the Eddington limit. The basic argument is just, again, what's inside versus outside. So you really only need a small duty cycle of time. You just need to occasionally have a black hole get lucky. Yep.
What is the denominator, the number, the 50 million?
Oh, that's just the doubling time for something accreting at the Eddington limit with a radiative efficiency of 0.1. I left out the radiative efficiency terms, which also appear in there just for simplicity here. But so that's like for a typical radiative efficiency of it that we think most black holes are around of like 10%. It takes about 50 million years to double your mass accreting at the Eddington limit.
Yeah. And so how well do we know that the accretion happens exponentially? Like it's not a
that's just a mathematical statement, which is just a pure statement of if you are accreting in bursts that are at a fixed fraction of Eddington. Of course, in reality, you'll have a broad spectrum of lambda eds and F duties where you're accreting at many different rates for different amounts of time, right? And your function will be some integral over time of that, basically. This is just to toy modelize it to give you the intuition. Yeah. Mm-hmm.
How do we observe the super Eddington? Because for all the things that we observed so far, none of them show as super Eddington if you believe the black hole experiment.
Well, I think the challenge is that, as you, I think, know well, most of the models predict that you don't really get super Eddington luminosity even when you get highly super Eddington accretion rates, right? The Eddington limit is really a statement about luminosity, not about accretion rate. And the spectrum, it's only in these sort of second order details that the spectrum is predicted to start to differ in the super Eddington regime. And I think certainly some people have argued that we do have some evidence for that in terms of, potentially, spectra that show evidence for cooler, more extended envelopes. There's arguments about potentially maybe being able to use like C4 equivalent width versus blue shift to diagnose super Eddington accretors. But these are all pretty speculative because it's hard modeling, and I don't think we have good forward spectral models yet of what the more detailed spectral signatures of those accretion states would be. And that's something we're definitely trying to work on.
Whether we can find this.
Yes, I completely agree. And I think that's something that there's several groups, I think, trying to work on that problem. And I think there will be progress from these simulations, but yeah, it's a great question. All right, so the question then is, can this happen? Well, I'll just briefly mention before talking about it in a little more detail in a few slides. This is something that we've tried to look at. A former student who's now at CETA, Yanlong Shi, and a former postdoc who's now faculty at UCSD, Kyle Kremer, looked at idealized simulations where you just throw a bunch of small mass black hole seeds, small in this context meaning 1 to 100 solar masses, things that we know nature can definitely make, basically. There's no ambiguity that nature can make those into things like different molecular cloud, galactic nuclei environments that, again, are all conditions that we know nature can make. Some are more extreme than others. Some are like the centers of starburst galaxies, but none of them is more extreme than ARC-220, for example, a nearby starburst galaxy that's very well studied. And just ask, can they accrete? And it turns out some fraction can. Maybe it's only 1% of the seeds get lucky and are sort of in the right place at the right time to accrete a very dense clump of gas more rapidly than that would fragment and turn into stars. But you can get, these duty cycles up to sort of 1,000 times Eddington of percents.
This is just the Bondi rate.
Yes, that's the Bondi capture rate. We're not following the whole process all the way down. I'll talk about that's what much of the talk will be about, is sort of zooming in on that. Now there are alternatives. We have also looked at these more massive seed ideas. Yanlong also looked at sort of runaway mergers of stars, but we found that really wasn't that efficient at giving you very, very massive black hole seeds. Another former student, Chuijian Shen, looked at if you look at some exotic dark matter models, then you can skip the line entirely, go directly past GO and get to a billion solar mass black hole through exotic physics. But I think, this is, here we have to say that there's physics beyond the standard model. So it's fun to speculate about, but the burden should be very much, the prior should be very much that that's not the obvious answer. But one of the challenges is when you do this and you ask about early growth of supermassive black holes, a new problem has emerged. It's not just about time scales. It's become very much widely recognized in the galaxy formation community that galaxies pass through in their early lifetime this incredibly bursty, chaotic phase of growth, where basically the galaxy at higher redshifts is a train wreck. This is an image in a simulation of a Milky Way mass galaxy that actually forms one of these beautiful thin disks at redshift 0 that looks just like a real galaxy. But at high redshifts, this thing was a total train wreck. Gas is accreting in a very clumpy, messy form. Its multi-phase feedback from starbursts is blowing up the ISM. There's constant mergers and chaotic accretion happening, and there's no disk whatsoever. And in fact, we've seen that there's a very striking transition between this sort of chaotic phase of bursty star formation and the fact that the stars that form during this phase are in a very thick disk or spheroid type configuration, and that the thin disks don't form until you sort of settle out of this phase. And we now, this has become a hot topic now because Gaia has now seen very striking evidence for this transition. This is one of the few things that I think in the galaxy formation was very clearly predicted by simulations several years before it was observed. These transitions, specifically in some of the observations in the last few years. And it's also been argued that these bursty phases are necessary to explain things like the apparent excess of bright UV galaxies in JWST at high redshifts, that can very naturally explain why you have so many UV bright systems. And that's the student, Chuijian Shen, again, who's written papers about that. But the problem is, if you're in this chaotic, messy phase where your galaxy is doing this is a simulation by Daniel Anglaz-Alcazar of showing the black hole dynamics in these proto-galaxies. And this is work by a student, Linhao Ma, who's now at Princeton, who looked at the dynamics of these black holes. As you might guess, in these clumpy galaxies, where everything's time variable, the black hole is just getting scattered all over the place. It's getting flung around everywhere. And if your black hole is free somehow, if you just had a lone black hole, even if your black hole was 1 million solar masses, it's not going to center on the galaxy and just sit there. I mean, first of all, you can't even define a center of the galaxy at those high redshift times. And secondly, the black hole, even at 1 million solar masses, is basically a test particle compared to these huge molecular clouds and star clusters that are scattering all around. So either you have to form your black holes even later, after the disk starts to settle. That doesn't mean later in the sense of redshift 1 or redshift 2, because these very massive galaxies could have already at high redshifts undergone this sort of settling transition where they form well-defined centers. Or you need to anchor the seeds in something like very massive dense star clusters so that they're protected in that environment until those star clusters can migrate into the galaxy center, carrying the black hole with them.
How much denser the gas in this galaxy compared to our galaxy?
At high redshifts or?
Yeah.
So the actual densities aren't wildly different. There's a lot more gas when this thing's a massive high redshift thing. So the gas fraction might be 50% as compared to 5 or 10%. So there's more. The density distribution, you know, the densest clouds, the things that are forming the massive bound star clusters get up to more like, maybe those are about 100 times as high a surface density as a typical GMC in the solar neighborhood, like 10 to the 4 solar masses per square parsec, which is kind of what the star formation community generally finds you need to get a bound star cluster able to form. So you can't really get some denser structures, but yeah, I mean, it's so inhomogeneous, it's a little hard to say overall. So briefly, you know, the student Yanlang Shi that I mentioned earlier recently had a paper I want to mention where I think he ran the first simulations that we're aware of that actually see a potential solution to this kind of play out end to end. And it's not that these have all possible scales resolved or physics in them, but at least they present a story that might reconcile this, which is basically you start from some gaseous star forming clouds that have low mass black hole seeds in them. Most of the time, if you're either a low density cloud or a low mass cloud or in a small halo with a shallow potential, or if you're metal free because you can't cool efficiently enough, then you're going to start forming stars, and the stars will just blow up this cloud and leave an open cluster behind. And that's what usually happens in star formation, especially in the local neighborhood. But if you're dense enough and don't meet these conditions, if you're dense and massive enough and have some metals, so interestingly, this is quite different from what Priya was describing. This won't happen in the very first generation of star formation. This will happen after sort of second and third generation star formation. It can help to be metal poor, but you can't be too metal poor. You actually need more efficient cooling for this mechanism to work. You can have this cloud complex fragment into very dense bound star clusters. And in the star cluster community, it's become widely realized that this is how you assemble a massive star cluster. You first fragment into many subclusters that rapidly hierarchically assemble with each other. Because you basically have, instead of stars moving under dynamical friction in a smooth potential, you have a series of sort of one-to-one mergers hierarchically happening of subclusters of comparable mass merge with each other, merge with the next layer up of the hierarchy, et cetera. And the beautiful part about that is it merges you break into these dense subclusters that are all whizzing around inside of this. That gives you a huge cross-section to capture any black hole seeds that are lying around in the centers of these subclusters. You anchor them in the subclusters. You then merge them all together in of order 1 dynamical time, because this hierarchical merging happens so quickly. Bring those black holes to the center. Now you've formed a sort of massive star cluster that in these extreme simulations is more like a proto-bulge. This is sometimes what we see happening in our cosmological simulations when you form the sort of proto-bulge, the proto-center of the galaxy, carrying a black hole with it, and then that can finally anchor that and start to give you enough external potential to have a massive gaseous disk start to accrete around that center and carry gas towards the black hole. And in the particular case study in Yanlong's simulation, this takes you from a 10 solar mass seed to a 1 million solar mass seed in what was a pure gaseous initial cloud that becomes about 100 million solar mass stellar protobulge in less than 1 million years. Now, again, we're not resolving the accretion to the horizon here. We're resolving it down to like the Bondi radius in this. So, of course, there's a question of how much gets through, what comes back out. Lots of interesting open questions, but this sort of scenario can potentially shepherd your black holes all the way down. Yep.
So
So I can understand this in layperson's terms. It's dense enough that you're getting large stars forming because there's enough gravity to allow them to continue to coalesce to maybe 100 masses, solar masses or whatever. They're very short-lived. Now you're getting the metallicity when they go supernova or whatever, which allows you cooling for the next generation, I guess. And so it's dense enough and massive that it's keeping it together.
Yeah.
Okay, and is that, you said it's over,
Yeah, so there's some.
what, over like 100,000 light years, 1,000,000 light years, what are we
So
talking?
this whole thing is happening on order, maybe 100 parsec scales or something like that, yeah. So it's more like, you know, this right branch would be more like a proto-galaxy nucleus in terms of its conditions than what we would think of typically as a molecular cloud in our solar neighborhood, which would be more like this branch of.
And this seed is growing not through accretion, is it doing mergers of?
It's mostly through accretion. There are some mergers that happen, although of course we again don't resolve the actual merging. It's mostly accretion.
But I mean, the time scale you mentioned in the earlier thing was, 5 to the 7.
Yes, so this thing grows wildly super Eddington. Now grows here again is captures into the Bondi radius at a wildly super Eddington rate. So again, yeah, that's the key, is that this has no Eddington limit, basically.
Is that spreading all the way or is slowly converts, I think at some point once things are.
Yeah, so as it gets big, it finally starts to calm down, and both because the black hole's getting bigger and because the accretion rates are dropping after you exhaust this initial gas disk, the Eddington ratio starts to drop, and this thing would get more and more of a challenge accreting. It's still below, it's interesting, in this particular case, it's below the M sigma relation, but above the M black hole, M bulge relation. So maybe in a self-regulated argument, it could continue to grow while the galaxy grows, but that's pretty speculative at this point.
And the feedback from this accretion onto these black holes on the, gas around is taken into account.
Yeah, so this model has feedback, but admittedly a pretty weak feedback model. So Yanlong has another paper that's a longer, more systematic study where he tries to look at basically how does feedback, what are the limits to how super Eddington you can go on large scales like these relative to say the Bondi radius or the accretion disk size based on the strength of the feedback. Of course, if you make the feedback large enough, you'll blow up any incoming accretion and self-regulate at lower black hole masses. So there is, these are, I'd say, plausible, but on the weak side. It's fair to say, the feedback strength that we assumed on large scales here.
But presumably that depends on how you implement feedback.
Yes, yeah, so.
Probably the advanced different feedback process.
Absolutely, and then his other paper was trying to survey that to some extent, looking at different energy injection mechanisms, also radiative versus broad angle mechanical versus a jet feedback model and how those regulate differently. So it's not like there's one, we always like to talk about there's like a magic number of the energy efficiency, the fraction of m dot c squared that gets turned into feedback. But what that will do will depend strongly on which of those forms it's coming out in and how it's coupling and where it's coupling in the medium. So those are all, still uncertain. And I'd say his other paper is a more comprehensive, this is a cool idea, case study, but his other paper is a more comprehensive study of, what are the, if it's this, what then kind of.
What kind of feedback model was assumed there?
I'd have to remind myself in the paper. I mean, it had some mix of radiation jets and broad angle alphas, but I don't remember the efficiencies, for example, that were assumed. It did assume that at super Eddington rates, the luminosity became radiatively inefficient, which is what the accretion disk models tend to predict, so that your L only rises logarithmically as m dot increases beyond some critical value, which is very important because if L just stays proportional to m dot, you blow everything out very efficiently on large scales. But I think nobody really predicts that to be the case. All right, so to wrap up this transition to the growth, since we're already getting lots of questions about the growth, I just want to remind people that high redshift supermassive black holes don't really necessarily favor direct collapse. They can have super Eddington accretion, in which case their seed masses kind of don't matter anymore if you're getting highly super Eddington. They can matter at a nonlinear level for how they capture gas initially, but it becomes much less dependent on the question of seed mass. And also this question of sinking, I think is really still an important thing to think about because they really can't sink during this early chaotic phase. So either they're forming after galaxies become more structured or they have to be anchored in some other structures and growing in those other structures until that happens. So let's transition to now talking about the more conventional times we talk about growth, where let's say we've gotten past this phase, the galaxy has started to have some kind of a center and it's funneling gas towards that center. We still want to know how the black holes grow. And there's a few, again, pieces of conventional wisdom I'm going to argue aren't always borne out. One is that fueling from galaxy scales becomes inefficient once the black hole starts to dominate the potential. Another is that if you try to fuel the black hole at super Eddington rates on large scales, the gas will undergo runaway fragmentation into stars, and stars will eat the gas before it can get to the black hole. And last, and what I want to spend most of my remaining time on is that the accretion disk that you form is something like a sort of Shkursky of 1973 or Novikov-Thorne type disk, where what I mean by something like that, I mean that there's an implicit assumption that the magnetic fields are sort of dynamically weak in the accretion disk. Just briefly to set this up, we've been, our group and myself have been interested in this problem of how do supermassive black holes get fed. My whole career, I've been working on this in one form or another. And it's a very multi-scale problem because, again, we know that black holes from various constraints grow. Most supermassive black holes grow primarily by a gas accretion. That gas ultimately comes from the cosmic web on megaparsec scales, but has to get down to AU scales to be accreted. There's 7 or 9 orders of angular momentum that the gas needs to lose in order to be accreted on those small scales. So when you ask this question, how do black holes accrete? Many conferences I've been at, I'm sure Shawie's been at, people have argued about this, and it means different things depending on the scales you're focused on, because really, there's different physics operating on these different scales as gas moves in. So on large scales, there's been a lot of progress from things like cosmological simulations and galaxy formation simulations, where we, I think, understand a lot better how gas accretes from the cosmic web onto galaxies. There's still very much active work on that through things like these cold filaments. Within galaxies, we've had ideas for a long time that I think are still qualitatively encompass many of the key ideas, that you have things like galaxy mergers and disk instabilities that cause non-axisymmetric structures and strong torques and shocks within the galaxy that allow gas to lose angular momentum and energy and dissipate and fall in towards the center of the galactic potential. On smaller scales, that can repeat, and you can form secondary structures. So famously, people talk about from this paper by Schlossman and Begelman, bars within bars, that you have this hierarchy of instabilities and non-axisymmetric structures. You might more generally call it, I think bars within bars is a little over specific. Elliot Quadert and I, we worked on this together when I was a postdoc at Berkeley, likes to just call it stuff within stuff, because it's really any non-axisymmetric instability. And we wrote a series of papers arguing, for example, that people worry that bars don't propagate through the black hole radius of influence because the bar doesn't can't support itself deep interior to a Keplerian potential. But that's fine. You just have different modes that can propagate through that barrier, basically. Things like M=1 modes, slow modes that people like Scott Tremaine first pointed out have no problem propagating through closer to the black hole. And I'll talk more about those in just a second, very briefly. But then you sort of have this gap when you get to sort of parsec scales and subparsec scales, where there's actually very little work on this sort of intermediate range before you get to the sort of true accretion disk scale simulations, where there's, of course, a very large community who've done beautiful work. Folks like Jim and others here have worked on this problem of understanding accretion going down to GRMHD scales, to true horizon scales even. So this gap is an interesting one. I mean, the challenge there is a lot of physics. It's not just the scales, but the problem is all of these are primarily, if you look at the numerical simulations, it's dominated by people from the sort of ISM galaxy star formation community using codes that are popular in those communities, because the processes you need to care about, like star formation, is important, and stellar feedback is important, but you can also make certain approximations, like we can certainly ignore GR. We can treat the cooling as optically thin, for example, assume cooling photons just escape to infinity from the gas, are very different from the approximations you have to make or can make down here, right? So most of these simulations for the most part, don't care about star formation. You're not worried about self-gravity at all, usually, if you get close enough to the black hole. So you might not even include self-gravity in these calculations of the gas, and that's fine, let alone in things like stars and other things like that. But of course, there's lots of physics you need to care about. So if it's high accretion rates, you'll work with complicated radiation hydrodynamic simulations. You definitely need to include magnetic fields in these calculations. And as you approach the horizon, you need to include relativistic effects in these calculations. But until recently, it's not really been possible to sort of bridge this gap, in part because of just having all of those physics in a way, in the same code in a way that can interpolate across those numerically. And even analytically, it's been hard because we weren't sure what reasonable approximations were to make in between. So on the large scales, I just want to mention very briefly, we've continued to work on these and try and connect it more all in one rather than breaking up the problem. This has been largely led by Daniel Anglos-Alcazar with a couple other folks in his group, Jonathan Mercedes-Feliz and Rachel Cochran, who basically developed a sort of super Lagrangian, you could think of it as the particle code version of adaptive mesh refinement with instead of assuming constant mass resolution elements, you just spatially refine on an interesting region more and more and more. And supermassive black holes are actually one of the easiest cases to do this because you have a very clear target that you want to refine on, basically. Just say, as a function of distance to the supermassive black hole, I have some adaptive resolution that I'll refine on at different times. And they've done this down to sort of subparsec scales using sort of standard galaxy formation physics. So that's why they have to stop at subparsec scales. It's not because we couldn't numerically push to even smaller scales. It's because our physics modules stopped making sense on significantly subparsec scales, the way they were implemented at the time in 2020 and 2021 when these papers and simulations were being developed. But from that, they were able to show that you can get very strong accretion. You can get phases with little accretion. You can get phases with very high accretion rates up to 10 solar masses a year by just zooming in at different times. They just zoomed in at different times in the history of a cosmological simulation of a massive galaxy. And then on large scales, the accretion was largely driven by this process we call gravitational torques that I'm not going to go into in this talk. But the basic idea, it's very well studied on large galactic scales, going back to the 1980s at least, is that you have mixed component disks of gas and stars that develop these non-axisymmetric instabilities like spiral arms and bars. And when you have a mixed disk with gas and stars, one of the unique features of this is that the stars and gas, their modes don't process at the same rate. You get offsets between the modes. Also, you get that the gas gets sort of accelerated into the stellar overdensity or vice versa. Sorry, I should have drawn, I swapped which one is stars and which one's is gas, sorry, in this plot. But you get the gas sort of falls into the stellar overdensity and can get driven into very strong shocks where you can do things like induce molecular cloud and star formation, but also very efficiently dissipate energy and get very strong inflows along those structures. So that part of the story, I think, is increasingly well understood. But we wanted to go further. So in this next set of experiments that just started being published a year ago, we've united some of our simulations that were designed to study star formation down to individual protostar scales with our galaxy formation simulations and with this refinement criterion to go all the way down into the sort of true accretion disk scales. So this is a simulation just showing a density plot falling in at one moment in time of what starts at megaparsec scales around a very massive high redshift galaxy. It's a redshift 4.5 galaxy that's got a massive starburst, 200 solar masses a year of star formation, giant clumpy messy train wreck with lots of merging happening, a big molecular cloud complex of 100 million solar masses gets knocked around and flung by the center of the galaxy where there's a pre-existing 10 million solar mass black hole that tidally tears a big chunk of that molecular cloud off, circularizes it, and forms this accretion disk. Going down to, in this case, this simulation went down to about 300 AU, about 80 AU or 300 Schwarzschild radii from the black hole. And it's not just, again, the question of scale, but there's a lot of the physics that had to be combined for this. So I'm not going to go through all of these, but sorry?
What is being plotted?
This is just a surface density projection. Yeah.
Of gas.
Yes, but with an adaptive scale, because otherwise, it'd just be white on the small scales and invisible on large scales. So there's some radial adaptive scale that is used here. And you can just very clearly see the accretion disk, the outer accretion disk here that forms. And again, this is a radiation MHD thermochemistry simulation with self-gravity, star formation, with individual resolved stars in the outer disk, et cetera. So we think we can start to bridge this gap in between the scales of these simulations.
What is unsolved for this disk?
So I'll show that in a second, but it's very high. It's the outer disk MDOT is about 20-30 solar masses a year, which corresponds to a couple hundred times the naive Eddington limit of this black hole.
So they start forming in the outer parts.
And the very outer parts are, but weakly so, less than you would expect potentially, for reasons I'll talk about in a moment. Yeah. So this is just another pretty picture, a static image showing the structure on different scales from the follow-up simulations that I'm working on the draft of right now, where we actually go down to, we just continue this process for these simulations in the newer paper down to the ISCO here. Now this is using just a Pachynski-Witta potential, so we're not doing the GR correctly. We wanted to go to smaller scales because for these high accretion rates, we were just outside with our previous simulation, the radii where radiation pressure should get really important. We wanted to see what the radiation effects would be as we pushed smaller. To really do the horizon scales correctly, there's another project which should be on the archive in hopefully a couple weeks, led by Nick Kaz, who's a student at Northwestern, where he took these further zoomed in simulations as initial conditions for their GRMHD code HARM, and has gone all the way to horizon scale GRMHD simulations. So, this is 2 gravitational radii, this is the actual, this circle is not, we deleted the inner part with a simple sync boundary. This is the real horizon here, where you can see these are field lines. You're getting a nice jet type structure forming and things like that.
This is with radiation.
This is with radiation, yes. He has some runs without, but now he has the runs with the actual data. And I'll show a couple quick results of his, but it's still very preliminary because we're putting together the draft right now. But the striking thing from these runs, though, is that Jim has heard me say this before in a previous talk I gave where he saw some of these slides, but we were kind of, the goal was to see an accretion disk, which we expected to be the standard textbook accretion disk type structure, and say, we did it. Great. We can, hand this off maybe as useful boundary conditions to people doing accretion disk simulations, but we're sort of done with the point of these zoom ins. What we did not expect is that the structure of this accretion disk is very different from what the sort of textbook accretion disk theory gives. And the main difference, the most important one, is that the magnetic fields are vastly more important. So there's this plasma beta parameter, which is just the ratio of thermal pressure to magnetic pressure. Here, whenever I say beta, there's different conventions in the literature. I'm specifically referring to thermal over magnetic, as compared to some people do thermal plus turbulent or thermal plus radiation. Here I'm just saying thermal over magnetic, sorry. Is 10 to the minus 4, with these very strong sort of toroidal or azimuthal magnetic field lines. So this is showing the gas wrapped up around the black hole with, you can see it's sort of wound up with these toroidal fields. And I won't go into details. You can look at all sorts of profiles. This is a fun face-on projection of different quantities where it's actually kind of hard to show things in a pretty way over like 9 orders of magnitude of spatial scale. So this was our attempt at showing a sort of log scale face-on projection of the disk from sort of ISCO to outer accretion disk scales. But the important things that where is, as I said, this magnetic pressure dominates over thermal pressure basically everywhere in the disk at very small and very large radius. And this is true in Nick's horizon scale simulation as well. Also, at basically all scales, the magnetic and turbulent pressures are comparable. So the turbulence is transalphanic, for those of you who care about turbulence, at pretty much all scales. And then in terms of the radiation, in the outer disk, the magnetic pressure is much larger than the radiation pressure, which you'd expect. You'd expect the radiation pressure to be very low in the outer disk. But in the inner disk, the two become comparable to each other. So if you include radiation, the beta of the inner disk is more like 1 which is similar to what people have seen approaching this problem from sort of the other direction. So, for example, simulations by Yanfei and Jim found similar results for accretion disk simulations in these sort of nearer to the horizon regime for super Eddington accretion disks. And we've also now got a suite that look at different accretion rates, and I'm not going to go into any details here except to say that most of the behaviors I'm going to talk about, with the exception of some of the radiation effects that are not scale-free, most of the effects are kind of scale-free with m dot over the range of about 1% of Eddington to about tens of Eddington. Again, with the exception of some radiation and thermal effects that you don't expect to be scale-free. The sort of disk structure is largely scale-free across this range. Below about 1% of Eddington, you start to see the same thing you predict for more traditional accretion disks, but the disk becomes optically thin to its cooling radiation, and this kind of disk can't be supported. And you probably transition, I would guess, to something like an ADAF type solution for those of you who care about accretion disks.
So is that just zooming in at different times, or how are you tuning?
So that experiment, we are trying to do the zooming in at different times to have a more controlled experiment there, since we're only focusing on the part interior to where the black hole dominates the potential. We did the much simpler experiment, which was take our initial simulation that went just inside that radius and just divide all the gas masses by a number so that it's a lower gas flux coming in. So yeah, much easier to do, not truly self-consistent, but good enough for starting. So how do we get to this state? I want to talk about that for a few minutes. So first, let me sort of give the conventional wisdom in more traditional accretion disk models. So you have your black hole. You start from some, often a torus of gas initialized around that black hole in some configuration, and you're not really, doing the ISM or thinking about the ISM's connection to this gas directly. Not that people weren't aware that this could be important, just that you're doing it, problem with some big scale separation. So you're focused on this part. So let's now take a little slice through that torus of gas viewed edge on. So here's our horizon, here's our torus viewed edge on. The usual assumption when we start things here for various reasons is that you start from some either you start from a beta that's very large, meaning a weak magnetic field. So you might start from a trace magnetic field and want to ask, how do magnetic fields get amplified in these disks? Can they get amplified at all? Or you might start from a vertically threaded magnetic field. And again, there's reasonable reasons why you might do this. And in some cases, this makes a lot of sense that you're talking about a disk around a star or a neutron star or something like that, where maybe this is the dipole field from the object. That makes a lot of sense. There's other cases geometrically where you might expect this to be the initial field configuration. But in either case, the point is whether you start from trace or start from a pure vertical field, gravity is pulling the gas down towards the midplane from this fat torus configuration. And if it can cool efficiently and lose its thermal energy, it's going to collapse because the magnetic fields can't resist the collapse in the vertical direction to a very thin disk. Until you build up such a high density in this disk that the thermal pressure increases to a value that can compensate the gravitational pressure sort of pushing the disk down. And that equilibrium in the outer disk is very thin. So a traditional Shakura-Sunyaev disk, even so-called self-gravitating turbulent disks, typically have aspect ratios of H over R about 10 to the minus 3, right? So these are paper thin disks. Okay. I can't draw it that thin on the cartoon because it just won't be visible. Then, of course, you have things like the instabilities like the MRI that give you a turbulent magnetic and velocity field that lead to some Maxwell and Reynolds stresses that allow you to have an effective viscosity, or in the turbulence literature, this effective alpha parameter that allows you to accrete inwards and causes the gas to lose angular momentum. But another corollary of this is that in these types of models, it's worth noting the accretion is sort of by assumption in these standard versions of these models, very slow. It's a secular accretion process. And in the outer disk, you can be talking about millions of dynamical times, meaning the accretion time, the inflow time of the gas can be millions of dynamical times of the gas. So it's a very slow process, typically in that scenario. But there's a lot of problems that we've known about for a long time with these kinds of models. So The outer disk is well known to be totally gravitationally unstable. It's what led to the development of what I mentioned as these sort of self-gravitating disk models. The Toomre Q is vastly smaller than 1, and this leads to this conventional wisdom problem I mentioned earlier that you predict it would break up into stars much faster than it would accrete, because the breakup into stars can happen on order 1 dynamical time locally for a self-gravitating system, while the accretion I just said takes millions of dynamical times. So accretion loses. How do you get gas through? There's also instabilities in the high m dot regime that people have talked about for decades, the thermoviscous instabilities. I'm not going to talk about those really in this talk. And then there's various issues observationally. So if you just had this, you would definitely not get anything that looks like a real quasar spectrum. That much is unambiguous. The thermal part would be wrong in the sense that you'd predict much too hot a spectrum from the most naive version of the model. The effective temperature would be an order of magnitude higher of the sort of quasi-black body component we see in real quasars. But you also miss all sorts of things that we see that indicate reprocessing of the gas. There's problems with the disk sizes compared to microlensing and other observational tracers, the disk structure and kinematic structure with new data from observations like gravity that I'll talk about in a second. And this is related to if you go to any AGN meetings, you've seen or read any AGN textbooks, you've seen cartoons of all of these phenomenological components. These are things that we know are there observationally that have been introduced sort of phenomenologically to explain what we see in spectra and variability and now increasingly resolved mapping of AGN. There's something like a dusty torus of clumpy dust that has a very large covering factor on the sky, H over R of order a half or so. The broadline region, where you have these broad lines emitted, where you have gas, multi-phase gas at intermediate ionization states. There's got to be a sort of thick layer of Comptonizing gas on top of this. In addition to, there's the sort of traditional lamppost corona for those of you who work on X-rays, but the hot type of corona these days is the sandwich corona, which looks like this, basically. That we have various reasons from X-ray spectra to believe must be there. And none of that is predicted per se by this model. But now let's come back to what we see in these large-scale simulations. Boundary conditions really matter for this problem. And again, this has been recognized in the accretion disk community. It's not that people weren't aware of this, but I just want to emphasize it as to how it sets the stage completely differently for the problem ultimately. So we have our galactic ISM on large scales and our black hole radius of influence, just where the black hole starts to dominate the potential over our parsec. And I said, you've got this big cloud of gas that gets tidally disrupted and sort of wrapped up around the black hole in these simulations. Well, if you initially have even some tangled magnetic field out here, could be ordered, it could be tangled, doesn't really matter. As this gas gets spaghettified and twisted around and tidally wrapped up around the black hole, so too are the magnetic field lines going to be stretched into this sort of toroidal spiral configuration. That's just geometry, basically, that gives you that. So you're going to see these sort of field lines. And that's exactly what we see happening in our simulations, just a lot messier. This is images of the simulations showing this sort of filament falling in and circularizing here and wrapping up. If you can, it's a little hard to see in the projection. These are just images of the magnetic field lines face on different scales. You can see it getting wrapped. And basically the spiral becomes more and more regular and more azimuthal as you go to smaller and smaller scales where it's been wound more and more efficiently. And other people have started to see this in simulations too. So I mentioned Yanlong's simulations from intermediate mass black holes. He sees it form a disk on much similar mechanisms, despite using very different physics in his simulations than the ones I started talking about here. And winding up this toroidal field. Minghao Guo has seen this on sort of intermediate scales, even at much lower accretion rates, at the, where we wouldn't necessarily expect these kinds of disks to be able to persist all the way down to the horizon scales, and he doesn't see it persist all the way down to the horizon. But at least in the outer disk, he sees something geometrically like this happening. And this is an example from a simulation zooming into a different galaxy from a student, Yash Tomar, who's working on this, where we see it happening in other instances. And so this allows you to both have the field geometry, but also the field strengths that are interesting as initial conditions. from sort of trace or expected, I shouldn't say trace, I should say from expected interstellar medium or intergalactic magnetic fields. So this is just showing the typical magnetic field strength versus distance from the black hole in this simulation. And the point is, these simulations don't put in an assumption about the accretion disk fields. The assumption about fields is that there's a trace 10 to the minute minus 15 Gauss fields seeded at redshift of 100 just to have something, because we just use ideal MHD in these simulations. You have sort of nano-Gauss intergalactic medium fields. You have those fields get amplified to sort of micro-Gauss in the interstellar medium, much like what we observe. That gets up to milligauss in the centers of the galactic nucleus, again, where we have a lot of evidence of similar strength fields, and continuing on. It's actually remarkably close over such a large range. Of course, I've got 10 orders of magnitude, you could fit a power law to anything on that big a scale, but it's strikingly close to r to the -1, the magnitude of B, which, we tried to see if there was a cute reason for that. I don't know if there is, but it's kind of fun to think about. But anyways, so you get this inner disk. So let's look at what that does. So you have this toroidally magnetized disk, where again, your sort of initial tangled field gets wrapped up and circularized. So now we've got our same torus, but with this strong initial toroidal field that initially has beta much less than 1. And why does it have beta much less than 1? Because it has this initial field, yes, but also because in the outer disk, the gas is cold, right? When we talk about these very low beta values, it's worth remembering beta gets really low sometimes, not necessarily because, B is enormous, but because T is really small, right? You're talking about molecular gas out here, right? So when the temperature is 100 Kelvin, thermal pressure can be really low, even if magnetic pressure is just kind of modest, basically. So in any case, you have these strong toroidal magnetic field lines. What happens now if we try and let this disk go? Well, gravity is going to try to pull it down. But of course, as you do so, now you're compressing the magnetic field lines. So magnetic pressure quickly builds up and resists sort of further vertical collapse of this structure at a quite thick configuration, remaining with beta much less than 1 and very thick. The key here is that you basically halt the collapse of this disk long before you reach this thermal dominated thin disk state where you would start from in these other configurations. And that's really important because I think part of the reason, there's many reasons, but part of the reason why people didn't think a lot about these types of disks earlier is because you cannot start from a Shikura-Sunyaev thin disk with a trace magnetic field or a vertical seed field and pump it up to this state by amplifying the magnetic fields. Energetically, you've already lost. The gas is so dense and so compressed in that super thin midplane, the amount of energy it would take to blow it back up would just destroy the disk, basically, from that state. So you're not starting from that initial condition and then going to this via amplification. Nobody sees that. We don't see that. You're really starting from this disk and never going through that other state is important.
You mentioned the temperatures of 100 Kelvin. I mean, how can you get an ideal MHD in this case?
So
non-ideal effects like polar diffusion and so on.
We actually included those in some of the runs that we did here. But even back of the envelope, these are the coldest gas does get down to 100 Kelvin. A lot of it's warmer than that, but also it's multi-phase. But even in the cold gas, because you're in this nuclear starburst. And there's a very strong stellar irradiation and self-irradiation and cosmic ray environment. The ionization fractions never really get below about 10 to the -2, 10 to the -3. So all these non-ideal terms are very weak, basically, which is very different from the circumstellar disk case, where those are hugely, I was just talking with UA about, we are working on that for circumstellar disks where those are really important, but just even back of the envelope, the time scale, like the ambipolar time scale is many orders of magnitude bigger than other scales.
Presence in this case.
Yes, yeah. And it has a self-consistent model for dust sublimation. So you actually resolve the sublimation radius and stuff. And you resolve the gas sort of self-ionizing as it goes in as well. Now again, there's definitely more complexity we could include in those calculations. I'm actually not worried about the non-ideal terms here so much for that part of it. I worry about it more for the star formation in the outer disk, where you get to even higher densities and more shielding within those clumps, subclumps in the outer disk, let's say, which are not as well resolved, of course, here. But yeah, so in addition to what I just said, another consequence of this is that you can show in these sort of vertically magnetically dominated disks that you have very strong Maxwell stresses that lead to very rapid accretion. So when we measure the accretion time in these simulations, the accretion time is of order 1 orbital time, right? So this is really dynamical accretion. Right? It is not secular accretion. It's happening really fast in systems. And that's important for a host of reasons. So you flow inwards very quickly, you have sort of comparable magnetic and turbulent pressure. And then, as I said, in the inner regions, radiation pressure is comparable as well. What's driving that turbulence? I don't know. I just list a bunch of ideas here. We're trying to investigate this in more idealized simulations, like the one that John O'Squire posted on the archive yesterday that we talked about. Which I think, as is often the case, only confused us more about this problem. So I don't have a great answer, and anybody who's done these multi-physics simulations knows it's incredibly hard to sort of extract why, the turbulence has the strengths that it does in these kinds of simulations. So I think there's a lot of work still to do. There's a lot of viable drivers of turbulence. But in the last few minutes, I want to just sort of say, why do we care about this? So of course, if you care about accretion disks for their own sake, you care about this. But even if you don't, this has a lot of interesting consequences that I'm just going to touch on briefly. So comparing the sort of standard disk to these, of course, one's dominated by thermal pressure, one's dominated by magnetic pressure, but also there's this difference in thickness. So you have a very thin disk versus a very thick disk. The turbulence is very different. So the standard alpha disk is sort of by definition more in the weakly compressible or subsonic turbulence regime. It's not truly laminar, but weakly compressible, whereas these disks are in the highly supersonic turbulence regime because the turbulence is transalphanic. And remember, the sound speeds are negligible because the beta is so small. These have fast cooling times and therefore are multi-phase, have very complicated thermal structure, whereas the sort of traditional Shikara-Tsunyaev disk is effectively uniphase with slow cooling. I mentioned the stresses are very different, but those stresses being different mean that the disk masses and densities are wildly different. So it's not just that the disk is much thicker when it's supported by magnetic pressure, but because if you have a much stronger Maxwell stress, then and you accrete much more quickly, this is accreting on 1 orbital time, this is accreting on 1,000,000 orbital times, which means if I want to supply the same mass flow to the black hole, I need 1,000,000 times more gas sitting out there in this model than I do in this model. So this is 1,000,000 times less massive, a disk, than this disk. So its opacity structure is completely different. Also, its gravitational stability is completely different. This disk is gravitationally stable at all radii, even out to several parsecs from the black hole, because it's so much less massive. And this also means, because you have this very thick lower density, so a lot of that stuff above the disk is optically thin, you get these very extended, cooler, sort of optically thin or intermediate optical depth reprocessing and scattering regions, basically. It's not just a black body sheet that's emitted, right? You have all this other structure. And again, we see that directly in the simulation. So if we take out the magnetic fields, we just get this razor thin disk that we predicted. And in fact, also we get, if you take out the magnetic fields, so here's, say, the inflow rate from this current simulation, just focus on the black line, which is like 10 solar masses a year, it plummets in the inner disk while the star formation increases, the star formation rate increases by a factor of 10 to the 5 or so when you take away the magnetic fields. So the magnetic fields are pumping it up and lowering the density and mass, which also resists gravitational instability and means that it forms stars at a greatly reduced rate compared to what you might think otherwise. They also have this multi-phase structure. So these are just some images that don't appear very clearly here that show that it's very multi-phase. This is just a movie showing, because it's been too long since I showed a movie in this talk, the same fall in, but now just showing sort of what dominates the pressure in different patches and different scales, whether it's thermal pressure or turbulent pressure or magnetic pressure dominating. And as you get towards the center, you'll see the disk is primarily magnetic pressure dominated, though there's still little pockets where, say, the turbulence is super alphanic and dominant, and maybe even some very tiny pockets where it's still got thermal pressure, but it's really dominant magnetic pressure as you go in. But these extended multi-phase components are really important for this question I mentioned earlier of all this stuff we see around AGN. So you can do more detailed models of that thermal and opacity structure, and what you get is that the inner disk, because this outer disk has such a big aspect ratio, half the light from this inner disk is hitting the outer disk somewhere. in the outer disk because it's this thick flared structure. And that means you'll get things like scattering. You'll also get reprocessing by partially ionized gas, which naturally gives you a patch of the disk that has a sort of scale height of 0.3 or 0.5 that has gas at densities of 10 to the 8 to 10 to the 10 particles per cubic centimeter that's partially ionized at temperatures about 10 to the 4 Kelvin, which anybody who works on AGN recognizes is what we have known for decades you need for the broadline region, the region that's emitting these lines. Likewise, you get sort of, illuminated dust out here, et cetera. And there's a student, Jaden Bardati, who's actually doing, full post-processing radiative transfer calculations on these simulations to make that into a real prediction of what the spectra look like to see if those really are reproduced at a plausible level. Nick Kaz has already done some initial, very crude estimates of where the emission would ultimately emerge from. Basically, what's the last scattering surface of photons coming out, where he sort of plots this distribution from his simulations of their sort of last scattering surface at the optical and compares it to microlensing sizes of AGN with similar luminosities, where the point is where these blue curves go to about half is where you would predict the sort of effective size of the disk would appear in the observations in the optical. It's very similar, at least. So it's encouraging that there's some qualitative consistency here. I don't have time. I had a couple slides going through this argument with Dalia Baron and Asha Piotrowska. We're writing a paper about how you can constrain whether or not there could be a hidden thin dense disk underneath all these big fluffy things at all. Because actually, when you look at your AGN cartoons, what we usually do is put all this big fluffy stuff with a little thin layer in between that we say is the Shakura-Sunyaev disk that's way denser than this stuff on top of it. But there's not really any evidence that there is a super dense sheet in the middle of the broadline region. And in fact, the paper we're writing up argues that there's actually a problem if you assume that, where the measurements of the kinematics from probes like gravity and the masers have gotten good enough that if the disk, because that disk, remember, has to be really massive to supply the required accretion rate, it would perturb the rotation curve to be highly non-Keplerian at these radii. You'd start seeing a sharply rising rotation curve at these very large radii that we just don't see. And you can use that to basically rule out certain types of disks. You can basically rule out a disk that's too thin and too dense at these radii. So, our preferred solution is just get rid of it. We don't need that actually. The real disk has been staring at us the whole time with all these big fluffy components that are there. The disk is all the components we have treated along the way from the observations, which looks a lot like what we see here in these simulations at a very crude level. If I imagine dicing this up into different chunks for that kind of comparison. Yeah. This was here just in case Jeremy came and wanted to talk more about the masses of the most massive stars that form in the disk. Roman is also interested in this and others. We do see a top-heavy IMF, but not super top-heavy is the punchline. I'm happy to talk about that later. So in conclusion, coming back to some of these big points, fueling from galaxy scales is proving more and more efficient as we look at it in more and more detail, including super Eddington fueling. But the accretion disk really is, in these simulations, looking like something very different from the classic model, at least in the outer disk radii, but with lots of work still to do. Again, this is all from the last year and in prep stuff, so very much in progress. This was just an advertisement that I have no time to talk about. We haven't forgotten about the feedback question. There's like 20 papers that we've worked on in the last couple of years, looking at AGN feedback on larger scales. About half of them led by Kung-Yi Su, who was at CCA and is now at the Black Hole Initiative. But there's a lot to do on that we're starting to try and build back out. So Nick part of his motivation of his project was to make the first predictions from these types of disks of how much jet power would actually come back out for us to include back into the larger scale simulations. So lots still to do, and I'll wrap up there. Thanks.
So, how much should, so for the low beta result, for example, how much should, you want to say anything about resolution?
Yeah, so as is always the case with these things, didn't do what I wanted to do, but give me 1 second. Resolution, is always a challenge for these because, you you always want more, and some of these problems are very difficult to convince yourself that you can sort of define any kind of truly rigorous convergence criteria for. That said, we've tried to do the best we can. So, first of all, these simulations are already much higher resolution than most previous simulations on these scales. So this is, for example, a plot of the scale height versus distance from the black hole, where these lines are different measures of the density scale height, the magnetic scale height, and the turbulence scale height that all kind of are similar at 0.2 or something. This purple line is the resolution length, right? So the scale height of the disk is resolved by, between, in the default simulations, 30 to 100 resolution elements, typically, the vertical scale height. Now, this orange line is the thermal scale height of the disk, which, because the disk is so cold, is much harder to resolve. We did some experiments where, unfortunately, we can't just make the resolution another order of magnitude better because we're already at the farthest we can push it. We can, however, cheat and move the thermal scale height up by just artificially putting a temperature floor in, which is this experiment here. It's a little weird because I used the isothermal temperature, so now this orange line is doing this.
That's the same plot, just with
Yes, and I cut out the inner regions just to be able to focus on the outer disk in this test problem, basically. And what we see is that it stays thick even when we force so now we know we're resolving the thermal scale height in this particular setup fairly easily, but it's still smaller than the magnetic and density scale height. So it's not a simple switch there. This is a plot from Jono's recent paper that we mentioned at the the coffee yesterday, where these are idealized shearing box simulations where, again, this is challenging. Here you can do a much more controlled resolution study, and it's not a totally monotonic trend with resolution. So beta, as you go from very poor resolution to good resolution, beta in the midplane goes up. The magnetic fields get less fractionally important, but then as you go to higher resolution still, beta starts going down again. And yeah, I think more work needed, clearly.
It is only sort of one sharing box.
Yes, in this case, it's not going to these very low values here. So we're trying to do some more controlled simulations to reflect that regime. We're also trying to see if you have other sources of turbulence keeping the disk puffed up, what that does. Because it's clearly, in these simulations, some of the behavior of beta is very related to the behavior of the turbulence in the midplane. And there's this whole list of possible turbulent drivers in the full physics simulations that aren't there in these idealized cases. So again, I think this is right for further study, definitely.
In your last slide, actually, you kind of alluded that it's a very complicated problem, this question of feedback. But I was wondering if you had spoilers or something, to some extent, if you think it'll get much stronger than maybe current cosmological hydrodynamical simulations have implemented in their prescriptions. And I just ask this because, there are some claims from cosmic shear surveys that you need actually much more extreme feedback or, much stronger suppression of the power spectrum than what hydrosims have been able to predict so far.
Yeah, I think the problem is, so on the galaxy scale, when we started this FIRE project, our goal was to really take a default model and see how far you could push it. And we focused on dwarf galaxies through Milky Way mass galaxies where you didn't have to worry about black hole feedback to first order, we felt. And there, of course, you have stellar evolution as your default input, which has a lot of uncertainties, but at least order of magnitude is well defined. With AGN, of course, we don't have that anchor point. So a lot of these studies are surveys of what if we put more or less energy into this or that form of AGN feedback. And I think what most of these studies focus on is, I think as compared to a simulation like Illustris that has sort of one AGN feedback implementation, which is more phenomenological and just hydrodynamic. In these simulations, so for example, if we want to look at the effect of relativistic particles or cosmic rays, we actually can explicitly integrate the equations for cosmic rays interacting with gas with uncertainties about some of the coupling coefficients that are huge. Likewise, if we want to do radiation feedback, we can do a rad hydro simulation. So most of these papers I view as studies of trying to make the predictions of if the feedback on these scales is really in this form, what are its effects that are different from other forms, and what are the observational signatures of that? So there's certainly ones that are easier to hide. So for example, one of the things Kenny's worked on is, if you have jets that get out of the galaxy and then accelerate a lot of relativistic particles, cosmic rays at large radii at their termination shocks that then diffuse through the sort of circumgalactic medium and solve the cooling flow by sort of a more diffuse process like that. You can hide a lot more energy than if you're trying to just launch winds directly out of the central parsec, right? So we could have a lot more energy through a source like that. But of course, it will couple differently and it will have different effects because it won't basically do anything to the galaxy in the immediate sense. It might indirectly affect it by starving it of new gas supplies, for example. So I think some of these channels could hide stronger feedback than the current conventional wisdom from the observations suggests. But I'm not prepared to say I trust any of them as the ground truth because we're just taking parameters at this point, as guesses. And I think, even for studies where you try and measure something like from the GRMHD simulations, the kinetic energy of a jet, let's say, the problem is a lot of jets, transfer a lot of their energy to the interstellar or circumgalactic medium at these intermediate scales when they're sort of first encountering the interstellar medium, which is in this same zone where there, as I said at the beginning of my talk, there's not a lot of work. And I think we really need to continue to bridge those scales back out now to do this. So I know that's sort of a cop-out answer to your question. I think you can do it. But at the same time, I'm not going to put a lot of money on any one specific mechanism yet that I'm not convinced yet that one of these is so clearly better at explaining the observations that it has to be right.
Yeah, so the question about scales, what's setting the separation between the more chaotic filamentary structure and the central disk?
So a lot of that's simply it's a good question. The most important thing is simply the radius of influence of the black hole, where the potential transitions from sort of self-gravity dominated to Keplerian, right? So the larger scale structure is a massive GMC-like complex. And honestly, most of the star formation and dynamics in that is not that different from a scaled, more extreme version of what you would predict in the solar neighborhood. It's turbulent, transalphanic turbulence. It's got beta less than 1 because the gas is cold molecular gas. It's a bigger star-forming complex that'll probably leave behind a massive star cluster, but it's not fundamentally wildly different from what
Okay,
we
so
might
that
expect.
means there are also many other accreting cores in that region, right?
Yes.
Besides the black hole.
Yeah.
The black holes.
Yeah.
Okay.
And again, in this case, it's during this chaotic clumpy phase where you might expect that it's more about encounters with these big complexes. It could be very different once you enter this relaxed phase. Like in the Milky Way today, it could be fed much more, on large timescales, semi-continuously from smaller structures migrating through the smaller gas clouds and filaments migrating through the disk, for example.
Okay, so that means the material accreted from the large scale, actually they are digested not only by the black hole, but also largely by the other accreting star formation core.
Yes, so star formation is an important sink until you get to those subparsec scales where it starts to get suppressed by a combination of tidal forces and thermal pressure and magnetic pressure. And that's actually one of the ways that we know that, this run where we turn off magnetic fields and the star formation does sort of uncontrolled run away. It's not just that gives you very little accretion onto the black hole. That produces a very steep cusp of stars in the center of the galaxy, much steeper than we see in the centers of real galaxies. That runaway needs to be suppressed at some level just to explain observations of stars in galaxies.
Yes, I asked because I'm thinking about the scaling relation you mentioned about the B spans as a function of like inversely proportional for R. I mean, usually if you think it's a steady state about accretion of black hole, then it's not really a steady state, but you should expect 1 over R squared. But if you think that there are also many other accreting cores in the region, then at a large radii, the amount of accreting material, I mean, they are not only consumed by these black holes, but also by much more other cores. So then you have to
Absolutely. And there's a big range here. I mean, this is partly because, as I tried to be honest about, when you plot something on such a huge dynamic range, it can look like a line when there's actually quite significant deviations. And also the scatter is quite big, in the ISM, you've got a couple orders of magnitude scatter. There's not one value of the magnetic field at the solar circle from the galactic center, right? It totally depends on what phase of gas, what densities you measure it in, right? And that's partly reflected in this scatter here. And so, I don't think that there has to be a simple causal reason why this would converge to r to the -1. I just thought it was kind of cute. Because I like integer power laws, we all do.
We can have last question.
So I have a question about the seeding and the feeding of these black holes, in the ISM conditions of these early galaxies. So you said the gas densities and from the temperatures are not very different from what we have in our own galaxy. And you are getting these black holes which are accreting at super rates and growing extremely rapidly. Now in our galaxy we have about several tens to 100 billion black holes floating around through the ISM. We see none of them.
Yeah. So I guess what I would say is, sorry, it's not showing. I was trying to page through this, but because I have to, I have to switch my screen share, I think, to show. So I think I probably wasn't being very clear. So while the range of densities, for a lot of the median gas is not that different from our galaxy. You are at these high redshifts much more commonly populating this tail of really extreme structures. So in this picture for the outline here with Yonlong stuff, this more typical channel where you just get an open cluster, an OB association type thing that doesn't have any interesting dynamics. This is going to happen in essentially every nearby cloud and almost every cloud in the Milky Way. Maybe the brick is an exception to this, but even the brick, it meets the surface density criterion here, but it's 4 orders of magnitude too low mass for this mass criterion, right? So there's really no cloud in our galaxy that meets this criterion. That said, if you go to massive high redshift galaxies, there are commonly, order 1 number of structures. It's not most of the entire galaxy, which was part of why I answered, but it's not so different in the median properties. But, if you look at a Milky Way mass galaxy already at Z of 5 or Z of 4 in ALMA, the median galaxy has an order 1 number of big clumps that meet these criteria, basically. So I think that's the difference, is you have these extreme things. There are nearby galaxies, though, that do meet this, even though the Milky Way doesn't. So, the center of ARC 220 handily meets this criterion. So we would predict that there should be some seed black holes potentially undergoing runaway accretion in the center of ARC 220. Yonlong did some back-of-the-envelope calculations. Unfortunately, compared to the luminosity of, it's all going to be Compton thick because it's all deeply buried. And compared to the luminosity of star formation, even if these things are accreting as fast as this simulation, it's about 1% of the bolometric luminosity coming out of those central regions would be from these black holes. So it doesn't mean it's impossible with spatially resolved studies to detect some embedded things that might be doing this in nearby galaxies, but it's going to be challenging. But it does predict that, so I don't know about the Milky Way, but at least nearby galaxies, you could potentially see this. Does that answer your question mostly?
Well, to some extent, we have very dense molecular clouds in our galaxy. So, if a black hole would be passing through such a cloud, I mean, the conditions probably would be the same as in this.
Yeah, but again, you need dense and massive, and it's still only, bear in mind, I should also clarify, it's something like, even when you meet these conditions, you need a bunch of low mass seeds, because it's only about, at most, 1% of the seeds that still get lucky and get captured and get runaways. But again, you have a lot of stellar mass black holes, so that's not, I think, the craziest part of it. But I mean, you're right. And I think this is part of the art. All these IMBH and black hole seed mechanisms, you have to play this sort of delicate balancing act of explaining why has to explain that and also similarly why doesn't every globular have a big IMBH sitting at its center, right? A lot of them clearly don't, right? So it has to be more than you formed a dense star cluster at all, right? To do this. And again, that's why I think these are happening under very massive conditions where I'd call it more like that's why I was trying to use the term proto-bulge here, because this is so massive, right? At 100 billion solar masses in this complex.
I think we should stop here. It's much behind us. Thanks.